So, Jai students, so this is our first topic of unit 4, finite state machine, and the analysis part we will be covering today. So, before going to that finite state machine, we have to first understand the basics. Those basics: FSM introduction, then types of FSM, state reduction, analysis of clock sequential circuit, and this design of clock sequential circuit. This is the topic which we will be covering in next lecture. Okay. So, first 4-5 topics we will be covering in today's lecture. So, what is an FSM? It is an electronic state machine, or any kind of digital electronic circuit which is comprising of flip-flops. Okay. So, the presence of flip-flop is must. So, a combinational circuit cannot be considered as a finite state machine. That means the circuit has to be sequential and it must be having some kind of flip-flop SR, JK, T or D. So, any circuit which is having flip-flop can be considered as a finite state machine. Okay. So, that machine will be having some external inputs, some external outputs, and other than this inputs and outputs, some internal state. Now, this state, this term state we are going to use again and again in today's lecture. So, first of all we need to be very much clear about what this state is. Okay. So, by state we mean that output of the flip flops read together. Okay. Let us suppose there are 3 flip flops in a circuit. Okay. I am drawing a random circuit which is having 3 flip flops, any kind of flip flop might be there. Either it can be D flip flop, JK flip flop, SR, T, whatever. So, it will be a synchronous circuit first thing, that means clock will be common to all the flip flops. That means FSM is always a synchronous sequential circuit. So, there are let us suppose 2 flip flops and there will be, let us suppose the flip flop is T flip flop. So, TA and TB. Now, let us suppose this TA is getting input from this external input X and there is a AND gate, and this is, let us suppose it is connected to this QB bar. Okay. So, I am making random connections, and this TB, let us suppose it is connected to 1, and there will be output QA, there will be output QB. So, this QA is there and this QB is there. So, this QA and QB further enter an OR gate to produce the final output. So, this is a random circuit. Now, we are going to identify which is the input, external input is X, external output is Y. Now, internal state, by this internal state we mean that how many flip flops are there, output of those flip flops, if we read them together, that will be considered as state. There are 2 flip flops A and B, outputs are QA and QB. So, if we read these 2 values together, this will be the state of the circuit. If I say that QA is 0, QB is also 0, then the state of the circuit is 0, 0. If QA is 1, QB is 0, then the state of the circuit is 1, 0. Okay. I hope it is clear that what the state means. So, there are 3 things: external input X, external output Y, and internal state means output of the flip flops. So, in our previous units, when we have prepared the sequential circuits, we have prepared counters, we have prepared registers. In none of these circuits, output of the flip flop was going somewhere else and the final output was the flip flop output only. Okay. So, in that case external output was not there, but in case output of the flip flop is also going into some other combinational circuit to give the final output of the circuit, that will be considered as finite state machine. Okay. So, these are the 3 things. So, output and next state depends on applied inputs and current state. So, you can check that this final output is dependent on, we can see that this Y is dependent on QA and QB, and indirectly these QA and QB are dependent on this X. So ultimately there are three factors which derive the output. Output and next state depends on the applied input, whatever you apply here at the X, and the current state. Current state means the output of the flip flops. Okay. So let's proceed further. So before going further, we will be using these things again and again. So I am summarizing in case you have not summarized it. So we will be using the truth tables of all flip flops. So in very short, if we check the truth table of SR, it will be 0 0, no change, 0 1 0, 1 0 1, and it is invalid. Similarly for JK, zero 0 will be no change, 0 1 will be 0, 1 0 will be 1, and 1 1 will be toggle. That means Qn plus 1 will be Qn bar, complement of the previous stage. Okay. Then excitation table, sorry, then SR is covered, JK is covered, then T. If T is 0, output will be changed, output will not change. That means if T is 0, output will be same as previous, and if T is 1, the next output will be the complement. Similarly for D, if you apply 0, you will get 0, if you apply 1, you will get 1. So these are the truth tables. Now covering the excitation tables very fast. I am writing it here because we are going to use them in our coming contents. Okay. So for SR, this is the excitation table. For JK, the excitation table is this one. For T, excitation table is this, and for D, this is the excitation table. So these four excitation tables we are going to use in our coming contents. So I have summarized them here. So in case you are having your notebook, you can have that page open instead of using these contents, because you will be needing those at the time of when we will be solving the questions. Okay. So characteristic equation, simplest one, Qn plus 1 is equal to D for D flip flop. Okay. And Qn plus 1 is equal to S plus R bar Qn for SR flip flop. Qn plus 1 is equal to J Qn bar plus K bar Qn for JK flip flop, and Qn plus 1 is equal to T XOR Qn for T flip flop. So these are the characteristic equation. Now definition of state, I have already told you. We can write it as outputs of all flip flops read together. If we read output of all the flip flops together, then it will comprise the state of the circuit. Okay. So these are the basics. Now we can start to our main topic, which is FSM. So FSM is of two types. First one is Mealy, second one is Moore. So first type circuit. So in your previous slide, you can see that here there is a input gate. I am changing the color. Input is input combinational circuit, because this AND gate is a combinational circuit. Combinational circuit. This is output combinational circuit, and this is flip flops. These are flip flops, and if flip flops are together, we can refer them as resistor. Okay. So these are three components. Now if these three components, you can see that next state combination logic, or we can say that input combination logic. There is an input, let's suppose it is X, this input is entering combination circuit, output of this combination circuit is entering state resistor. State resistor means flip flops. So this input through a gate, in our previous case, in our previous example, that AND gate which was used for the input can be this combinational circuit. or any other complex combination circuit can also be there, but for the time being this AND gate can be referred as this combination circuit. Output of that AND gate derived the flip-flops. Flip-flops output was in some output combination circuit, which was in our example it was OR gate. Okay, so these three things are common in Mealy circuit and Moore circuit. These are three things: next state combination logic, state register, and output combination logic. The only difference between the Mealy and Moore is that this final output, if this final output is also dependent on the external input, that means in Mealy type final output is dependent on state plus external input. Okay, but in case of a Moore circuit, everything is same. Everything is same. Next state combination logic, which in our case was an AND gate. State register, that means series of flip-flops. One flip-flop might be there, two flip-flop might be there, any number of flip-flops can be there. Then the output of those flip-flop entering a combination circuit, in which in our case it was an OR gate. Okay, and this final output is independent of the external input X. Okay, that means this final output combinational logic is independent of the external input, this X. This X has no role in finding the final output. So what is the basic difference between the Mealy circuit and Moore circuit? In Mealy circuit, final output is dependent on state and external input, but in Moore circuit the final output is dependent on only on the state of the circuit and it does not depend on the external input. So this is the basic difference. So summarizing the difference between Mealy machine and Moore machine. So first thing is this block diagram, which we have already covered, and from that block diagram we got to know that outputs are a function of inputs and states, and in Moore type circuit output are function of state only. It is independent. This input is not there in Moore machine. Okay, and then outputs usually specified on the state transition arcs. This is a new thing which when we will be preparing, when we will be covering the circuits, when we will be designing the state diagrams, we will see that in those state diagrams, the output usually specified on the state transition arcs. This is a new thing which when we will be covering the state diagrams, we will see that the output is mentioned graphically in that state diagram. Okay, so the representation of output is different in both the types. So when we will cover the state diagram, this point will be much more clearer at that point. So I am leaving it here only, but when we will be designing the state diagram, we will get to know how these things take place. Okay, so then state reduction. This is our first topic, state reduction. This is actual first topic which is asked in 10 marks question. So the content which were covered before that, what is the state, differentiate between Mealy machine and Moore machine, all these questions are of 2 marks only. Okay, but this is a question for 10 marks. So a state diagram is provided. State diagram, like we have mentioned here, that definition of state, in that I have said that output of all flip-flops read together. So those outputs can be 0 0 0 1 1 0. If there are 2 flip-flops, then there can be 4 different states. If there are 3 flip-flops, then there will be 8 different states. There can be. How many will be actually there? We have to check that. Okay, but maximum for two flip-flops, maximum states can be 4. For 3 flip-flops, maximum state can be 8. For 1 flip-flop, maximum state can be 2 only. Okay, so this is the basic of state, and these states can be easily referred as only alphabets only. So if this 0 0, I can say it is state A, this is state B, this is state C, this is state D. So there are different states, state A, state B, state D, state D. Okay, so these are the different states. So this is a question, 2 states A and B are equivalent, we have to reduce, like we have used K-map to solve the Boolean expression, to reduce the variables in our expression. This state reduction technique is used to reduce the number of states, because if there are lesser number of states, we will be requiring lesser number of flip flops. So if I say that a circuit is having 5 states, then to represent 5 states I will be requiring, 5 means 0, 1, 2, 3, 4. So that means 3 bits will be required to represent 5 states. But if somehow I am able to reduce one state and that 5 state becomes 4 states, okay. So to represent 4 states I will be requiring only 2 bits. That means I will require only 2 flip flops. So state reduction can help in reduction of flip flops in the actual circuit, okay. So that's the purpose of state reduction. So if we are able to perform state reduction successfully, we might be able to reduce the number of flip flops used in the circuit, okay. So this is a state diagram which is provided to us. A state diagram means that a circuit is in state A, okay. So if at any point of time, you feel that you need to repeat, you need some kind of revision in that state reduction topic, आप chat box में बता दीजिएगा, ठीक है. You can give me an indication in the chat box, I will repeat that step. So you can check that there are states A state, B state, C state, D state, E state, F state and G state. So I am preparing the state table. Present state. Present state can be A, B, C, D, E, F, G, okay. Next state, now this next state can be different for, if my input is x is equal to 0, next state will be different. If input is x is equal to 1, so if input is 0, next state can be different. If input is 1, next state might be different, and in those cases output can also be different. Output for x is equal to 0 and output for x is equal to 1. So this is table which we are going to prepare. So this is the first step. We have to convert this diagram into a table. So from the diagram we saw that there are 7 states A, B, C, D, E, F and G, okay. Now if we are moving from A state to B state, we are writing something here 0/0. That means if I am in A state and this is the input, if I receive an input 0, output will be 0 and the new state will be B. Similarly, if I receive 1, the output will be 0 and I will reach the state C, something like this. So I am in state A. This how we are going to read this state diagram. We have to check the contents on the arrow. On each arrow we are having 2 values, a value / value. The first value is the input, second value is the output. So in A state, if I get input as 0, the next state will be B and output will be 0. Similarly, if I go back on the left side, if input is 1, the next state will be C and output will be 0. So you can say that output is same in both the cases, but next state is different, okay. So here we can check that 2 states A and B will be considered identical. We have to find the identical states. If we find that the states are identical, we can remove any one of those states, okay. So if 2 states A and B are equivalent, कब उन्हें equivalent कहेंगे? When each possible input produces the same next state and the same corresponding output. So if we are in state A, I get input 0, I reach stage B. If I receive input 1, I reach stage C, okay. And that same behavior is also given by a state called D, then those A and D can be considered same, okay. So we can prepare this diagram now. You can check. . So in A state, you can check here, if you are getting 0 input, you are re-entering state A. That means next state of A is A only, and next state of A is B when input is 1, and in both the cases output is 0. Okay, 0/0, 1/0. That means in both the cases output is 0. So both these are 0. Similarly, if we check B, if you get input 0, you will get output 0 and reach stage C. If you are in stage B, you get x is equal to 0, you will reach stage C and output will be 0. And here, from here you can check that if input is 1, you will reach stage D and output is 0. Similarly, if you check C, this here, you can see input is 1, output is 0. Input is 1, output is, input is 1, you are reaching stage D and output is 0. And the second branch from C is here. If input is 0, output is 0. If input is 0, output is 0, and the next stage is A. Okay. Mohit has asked one question. Mohit is saying, here we are grouping same input states. No, we are not grouping the states. We are just checking whether one state behavior is identical to another state. If we find that the behavior of one state is exactly similar to this second state, then one of these states can be simply removed from the table. Okay. So let's proceed further. D. We are in state D. If I get input 0, then I will reach E and output is 0. In D, if I receive input 1, I will reach F and output is 1 here. You can check that. Similarly, if I check E, in that state E, you can check here. If input is 0, E becomes A, output is 0. And here, input is 1, output is 1. That means F and 1. Similarly, if you check F, here 0 0, that means if you apply 0, that means x is equal to 0, next state will be G, and for x is equal to, and in this state output is 0. And for this branch here you can see, if input is 1, output is also 1, and next state is the same as F. That means F is not going to change. F next state will be F only if in case you apply 1, and the output will be 1 here. Last G, this 0/0, that means if you are in G and you get a 0, you will reach A and output will be 0. And here this second branch of G, 1/1, that means if you get input as 1, the next state of G will be F and the output will be 1. Okay. So this is the first step, converting the state diagram into state table. Okay. So you can check which two rows are identically same. Which two rows are identically same? I am waiting for your replies in the chat box. Which two rows are identically same? You can check each and every, you can check those 7 rows. For if you find that for a single state you are getting the same next state and the same output, then we can say that these two rows are identically same. We can remove one of them. You can check row number 1, row number 2, row number 3, row number 4, 5, 6 and 7. So these are the 7 states. Which two rows are exactly similar? Which two states are exactly similar? Vijendra has replied B and C. Syed and Jash have replied E and G. E and G are exactly same. You can check E in front of E, we are having AF01, in front of G, we are having AF01. Perfectly correct. E and G are perfectly correct. That means state E and state G both are exactly same. So we need not to have both of them, we can remove one of them. Okay. So we can remove one of them. So I am removing G, because E and G are same. I am removing G from the table. Okay, so I am removing G from the table. Just give me a second. Hey. So this G I am removing. Okay, but I have to be careful. I have removed G because G is equivalent to E. So I have to replace this G. Sorry. G was written here. So I have to replace this G with E. Okay. Again you can check. Are there further more similar rows? Are there, now if I replace G by E, okay, I am removing this G now and using E here. Again you can check. Again you can check. Are there any two rows which are identically same? Are there any two rows which are identically same? Which are having the same next state and same output? Check these 6 rows. Are you able to find same identical states? Yash has replied 4 and 6. So 4 and 6, that means D and F. Isn't it? D and F. You can check that D and F both have same behavior. Next state of D and outputs are similar to the next state of F and their corresponding outputs. So again we can see that D and F are same. So I can remove F from the table as well. So I am removing this F. So this F I am removing. But I have to be careful from the table wherever F is written. I have to replace that F. I have to replace that F with D. Okay. Now again we have to see whether there are any similar rows, but now you can check that there are no two rows which are exactly similar, although there is similarity between C and E, because you can see A is here, A is here, D is here, D is here, 0 is here, 0 is here, but here 0, 1, a slight difference is there. For X is equal to 1, outputs are different. That means C and E are not same. And you can also check no two rows are same now. So this is the final state table. That means we have reduced the number of states from 7 to 5. Okay. So this state reduction, now we can prepare a fresh state diagram. So the final state diagram will be having 5 states A, B, C, D, E. So from A, now this will be very much clear to you. If it is clear, then that Mealy-Moore point will also be clear to you. You are in state A, okay, you are in state A. If you get X is equal to 0, you will reach A, sorry, if you get X is equal to 0, you will be in state A only, and at this point output is 0. Okay. If you get A is equal to 1 in A, you will reach state B for X is equal to 1, and at this point output is 0. So output is 0. Okay. So these are the two branches which are possible from A. Similarly, now check second row B. If you get X is equal to 0 in B, you will reach state C. You will reach state C if you get X is equal to 0, and at this point output is also 0. Okay. And if you have 1, you will reach state D if you get input as 1, and in this case output is also 0. Checking the third row, C's next state will be A, C's next state will be A for X is equal to 0, and output is also 0 here. C's next state will be D, that means C's next state will be D, C's next state will be D. I think it is clear, it is not getting obstructed with the corner photograph of mine. Okay. So if I get input as 1, I will reach D and output is also 0. Okay. Fourth row, if I am in D, I will reach E and output will be, for x is equal to 0, I will reach E and output is 0, and I will stay in D, I will stay in D only if x is equal to 1, but output will be 1. Last row, if I am in E, that means here next state will be A, here for x is equal to 0, output is still 0, and E to D, that means from E I will reach D if I receive input as 1 and output is also 1. So this is a reduced state diagram. Okay. So this is a reduced state diagram. Okay, I have repeated D twice. Okay. So we have to use D only once. So I am correcting it. This D I am removing because we already have a D. Okay. So from C to D, perfectly correct, by pointed out by Yash. So this C to D, C will enter, D output is 0, and from D it will go to E. If I receive input as 0, output will be 0, and D to D at x is equal to 1, output is also 1, and for E, E to A is already there, and E to D for x is equal to 1, output is 1. Okay. So I have corrected that. D was appearing twice, so I have removed one of them. Okay. So in this way we can deal with the states and how we can reduce the number of states and prepare a reduced state diagram. Okay. So this is the state reduction part. So now the next topic, which is very much important, is analysis of clocked sequential circuit. Very in this, it might be our first topic in which circuit is given to us. In most of the questions we have prepared a circuit as a final answer, but in this step, in these kind of questions, examiner will be giving us the question, examiner will be giving us a question and circuit will already be there, and we will be asking us what this circuit is going to perform. That means we have to prepare a state diagram that if this circuit is in this state, if you give 0, it will enter that state, output will be that, and from this state to that state, that means we have to give the behavior of the circuit, we have to depict the behavior of the circuit from this given circuit, and we have to convert this into a state diagram. Okay. That means, sir, we need not to design a circuit, we have to analyze the circuit, what this circuit is going to perform. So first is understanding behavior and type of the circuit. So if I ask you which type of circuit is this a Mealy circuit or a Moore circuit? Is this a Mealy circuit or a Moore circuit? So Mealy, Moore, I am going back to that definition. Here you can check that outputs are function of input and states, and in Moore output are function of state only. So look at this diagram, this is the final output. This final output is dependent on this x, this A and this B. Here it is x bar. Okay. So these are the three things on which my final output is dependent. You have to just check this final output and you can simply reply whether this is a Mealy circuit or a Moore circuit. So Syed has replied Mealy circuit, which is perfectly correct. It is a Mealy circuit because the output is dependent on external input. Straightforward reason accounting for this Mealy answer, that because it is Mealy because the output is dependent on external input x. Simple. So Jitendra has asked one question. Mohit has replied Moore it's not Moore, Mohit, because in Moore final output is independent of the external input. So this, if that x would not have been there, if a and b would have been there, x nahi hota wahan par, in that case this would have been Moore circuit. Okay. And Vijendra has asked a question, sir, what if no state matches with another? So we will consider that this state diagram is already a reduced state diagram and we will proceed with the further process. Okay. If no two states are matching, we will consider that both states, all the states are unique, we cannot remove any of the states, and we will proceed with the further process. Okay. So first step, analysis. You will be provided with a circuit and you can check flip-flop input equations, what you are getting at the flip-flops input. Second step, flip-flop output equations, what is the output of the flip-flop, and that output can only be determined by using the characteristic equation, because in that thing we have already seen that we can determine the output of any flip-flop if we know the inputs of those flip-flop and previous output. So here you can see that first step, flip-flop input equation. In the first step we will identify what is the input given to the flip-flop, and that input will be used to find the output of the system by using its characteristic equation, flip-flop output equation. But we will be very lucky if examiner gives me a circuit which is having D flip-flop, because we know that in a D flip-flop whatever is input, it will be the output, isn't it? Whatever is the input, it will be the output, because characteristic equation of D flip-flop is very much simple. Here you can see that for D flip-flop, Qn plus 1 is equal to D, that means whatever is the input you will get the same thing at the output. Okay. So if it is a D flip-flop, then this step, flip-flop output equation, it can be covered in the first step only, because whatever will be the expression for input, the same thing will be the expression for the output. So if it is a D flip-flop, it will be very much easy for us. But if it is SR, JK or T, in these cases we have to use the characteristic equation of the flip-flop. Okay. So this is the second step. Then third step is circuit output equations. Circuit output equation means this final Y, equation for this Y. Fourth step, preparing the state table. Fifth step is preparing the state diagram. So these two steps we will not be able to cover today, but first three steps are very much simple. Using these three steps, 20% of the question is taken care of, and rest of the things are very much simple. The sources of mistake are only in these three steps only. If we are able to write these three steps correctly, identifying the expressions from the circuit, then 20% chances are there that we will be able to solve the question perfectly. Okay. So you can check this D. First step, flip-flop input equation, that means I want to write input for DA. What is this DA? First flip-flop, it is output is A, this same thing is reaching here A, and this is A bar. I am writing all the expressions. This is X because it is X, this is also X, this is X, and this thing is X, and this is, here you can check, this is B. So this expressions becomes AX plus BX. Okay. So expression is AX plus BX. A and B are nothing but state variables. A and B are the state variables, because in the very first step we have seen that what is a state? A state means output of flip-flop taken together. There are two flip-flops, one of the output is A, one of the output is B. So if I read AB, so AB is the state of the circuit. Okay. So A and B are A, B and X, all three are deciding DA. Similarly, you can write expression for DB. DB, expression for DB is, you can check A bar is there, X is there, A bar X. Okay. A bar X, this is expression for DB, and this is that expression Y is written here. So this is, here you can see it is, if we, there are two sections here, this is also giving you y, and this is also giving you y, but you can opt for only one of them is additional here. So, I am not using this y, this is by mistake it has been put in this circuit, we are using this y only. So, from this expression we can check that y is a plus b plus this NOT gate, a plus b plus x bar. Okay. So, if we are using this y, we are getting this expression a plus b plus x bar. Okay. So, here step 1 flip flop input equation, this is flip flop input equation step 1, this is circuit output equation step 3. So, step 2 we need not to perform the step 2, why? Because it is a D flip flop, whatever is the input the same thing will be the output, that means DA expression AX plus BX which is the input of D flip flop, the same thing will be the output, that means the output the next stage, that means A plus, if we denote the next stage as A plus, so A plus will be equal to DA only, that means equal to AX plus BX. Similarly, B plus, the next state of B, this second flip flop will be exactly equivalent to DB, equivalent to A bar X. Okay. So, first and second step are exactly similar. So, these are the first 3 steps. Using these 3 steps we can write the state table. Okay, we can write the state table, but it would not be possible to complete this question. So, this is the first step and second step, A plus is equal to AX plus BX, B plus is equal to A bar X, finding the expression y, this expression we have y is equal to, we have used A plus B plus X bar, A plus B plus X bar. So, these are the first 3 steps, next steps we will be covering in our next lecture. So, if there is any query we can cover that, otherwise we can close the session and we will resume from this step only in tomorrow's lecture. थोड़ा सा रिवाइज करेंगे what this question was, what are these expressions, and we will restart from here only in the tomorrow's lecture. Okay. I hope it is clear, or if you are having any doubt we can cover in a separate Google Meet session as well. So, I think we can close it and let us meet tomorrow. Thank you so much.